Hello AP Mechanics students, welcome back. We reviewed Newton's laws in the last review video, and that was a very long video. It was probably I think close to an hour, and so we went over a bunch of different scenarios, different force diagrams, how to calculate acceleration, and again we were looking at the highlights. We didn't get bogged down in too many details, but it was a lot of information. And so today what we're going to do is look at Newton's laws again, and this time we'll use them with this little, what I call like a concept organizer, a basic cheat sheet of the various Newton's laws problems that you encounter, or common ones that you encounter on the AP test. So this is going to be included in the stream, so you don't have to copy this, but we're just going to go through the explanations. I'm going to zoom in a little bit because you may have trouble seeing the details of this. Some of these details are very small. No, zoom out, zoom in. Okay, so, all right, so something like this looks good. Okay, so again, we went over most of this yesterday, but we're looking at it again. The more times you see this in more different ways, the more likely you are to retain these things on the AP. So this is a force diagram of something that has its own ability to propel itself forward, like a machine or an animal. Machines have motors and gears and tires and stuff like that. People or animals have muscles and skeletons. So some kind of thing that accelerates doesn't need to be pulled by anything. So this is the force diagram of such a thing accelerating to the right. In the case of a person maybe running, the runner pushes the ground backwards, and the ground pushes the runner forward. Action-reaction, Newton's third law. So that's the forward force, the force of friction, the traction of the sneakers on the asphalt or whatever the person is running on. Of course, we got gravity and normal force also there, balancing each other out in a vertical direction. So there's only a net force in a horizontal direction. And as you could see, what I did is I put this force of friction within an arrow to indicate, so when you look at it, that that's the thing that's driving the object in the forward direction. In the next example, we have something passively pulled along, like if you're dragging a box or a crate or something. The crate doesn't have motors or muscles to propel itself along, so it needs a force from something else, you, externally. And so that is F applied pulling this box forward. It still has gravity and normal force. The earth pulls down with force of gravity or weight, and then the surface supports with a normal force, balancing out gravity so the box doesn't fall. But this time, friction isn't propelling the object forward. As it's being passively dragged, friction is actually inhibiting the motion or the acceleration. So I put it in a stop sign. You know, people know stop sign means, you know, you're slowing down to a stop. So this is tending to slow down the object to a stop. This is tending to drive it forward. So you kind of see the logic behind the symbols. And then the net force, therefore, is this applied force minus friction, whereas here it was just force of friction over mass was the acceleration. This is Fa minus mu F normal over mass gives you the acceleration. If I pull up at an angle, then this applied force, we have to think of it as having components. I drew the components in here. Well, I drew lines to represent the components. Remember, I've said this many, many times. On the AP test, when they give you a dot and they ask you to draw the forces, you would not draw these components in unless you want to lose points. So you cannot have the components. You just need the four arrows. The gravity down, the F applied up at an angle, the normal force up, and then the force of friction backwards. So the thing that's driving this forward is not F applied directly, but it's X component. So we take this and multiply by cos theta to get that forward force. This is F applied cos theta. The normal force is reduced because when I pull up at an angle like this, what I am doing is I am actually lifting up also. I'm pulling horizontally and I'm lifting. So that's, again, as I said in the previous lesson, if you got a 100-pound person, you lift up on them with 10 pounds, the normal force is only 90 pounds. So that's gravity minus the y component, F sine theta, subtracted from mg. So once again, to get the acceleration, you take this F cos theta minus the mu F normal, which is this. That's the net force. That minus that, divided by mass, gives you the acceleration. Okay, inclined planes, things on a hill. So, three forces. Once again, I drew this triangle in here. You wouldn't do that. And again, as I said yesterday or in the previous lesson, when you draw these three arrows for credit, if you want to draw components, you could do it right next to it. And that's fine. They're not going to take points off if in the margin here you draw, you know, the little triangle like this, right? So, not on this one. You're welcome to do it elsewhere. This is what they're going to grade you on, and so you don't put components there. Okay? But, three forces. Earth pulls down, normal force of the hill pushes up to prevent the person from breaking through the surface. And then there may be friction. Friction is what's inhibiting the acceleration, so it's in the stop sign. What's propelling this forward? Well, it's the horizontal or X component. Okay, usually we go X like this, right? But on an incline we go X this way down the hill. The X component of that gravitational force. This is the theta of the hill. So this is mg, the hypotenuse, times the sine of this angle. This is mg sine theta, minus mu F normal. That's what goes into the net force. Mg sine theta minus mu mg cos theta all over the mass gives the acceleration that's down the hill. If something is projected up the hill, so I take this and maybe it's like a box and I throw it, and while it's sliding up the hill, it's decelerating, it's slowing down. And I need to find the acceleration. This is the force diagram. Gravity, normal force, the same as over here. But this time the friction, rather than going up the hill because it's sliding down the hill, friction is down the hill because it's sliding up the hill, opposing the sliding. Now you see that the X component is backwards compared to the motion. So I put it in the stop sign also. And the force of friction is backwards. Both of these tend to bring the object to zero velocity. So when I do the net force, I do mg sine theta, that's that side, plus, not minus, plus mu F normal. All over the mass gives me the acceleration. Okay, next thing I'm going to look at. Okay, rockets or elevators. So in both cases, whether you're accelerating up or down, you have the same gravity force. In other words, if you weigh 150 pounds and you're in an elevator and the elevator is accelerating up or it's accelerating down, and I say, how much do you weigh? You're 150 pounds. That's the earth pulling down on you. The earth doesn't suddenly say, oh, the person's in an elevator, I'm going to pull more or less. It pulls the same amount, okay, that gravity. So it's m times 9.8. Both those vectors. See how I drew them in the same length. But if something is accelerating upward, like a person in an elevator, what happens is the floor is pushing up harder than the body weight of the person. So in pounds again, if this were 150 pounds, maybe this is 170 pounds, more than the 150. Then the person accelerates up. In newtons, maybe we got like 1,000 and 1,200, and so we accelerate upward, okay? So again, the normal force is what's creating the forward acceleration. I should also remind you that upward acceleration, you might be moving up and speeding up, or you might be moving down but slowing down. Upward acceleration again. Okay, so both those are upward acceleration. Okay, so I guess that kind of messes up with the arrow and stop sign business, but whatever. Okay, so downward acceleration. What happens is the floor of the elevator just eases up on you a little bit, so it allows the gravity to be greater. This never changes. That's m times 9.8. But the elevator floor, instead of maybe 1,000 newtons, it's only pushing up 900. So there's a net force of 100 down accelerating. So you put, for the acceleration, the F of g minus normal force equals, over mass equals acceleration. Okay, a couple multi-body problems, force diagrams. Atwood's machine, block 1 is more massive than block 2, and therefore it's heavier. Remember, heavy, weight, that's force of gravity. So I draw a force of gravity here on both blocks, but this one's longer. So on the AP, as I should have said back here with the elevator and the other problems, you do want to draw forces. If they are bigger, you want to draw them longer. Does it have to be exact? No, but you should draw them longer so you're showing the person grading that you understand how the forces are working. So FG is longer here because more mass. Now, this is rising as this pulley's turning. So how can it rise and accelerate upward? It needs more force up. That's tension greater than this. So this tension's got to be greater. So if this is like 5 newtons, maybe that's 7. But the Newton's third law applies. That comes from block 1 pulls block 2 forward. Block 2 pulls block 1 backwards. So if that's 7, that's 7. And then if this was 5, 7, 7, then this might be like 10 or something like that. So we have more force downward. So the tension's always between these two gravity vectors in value. Now to get the acceleration, F net over m. You could do this mg forward minus this mg backwards all over the mass. But what mass? Well, if we're treating this as all one system with what I call the shortcut technique instead of creating a system of equations, then we have to treat it as one object of m1 plus m2. So I'll say it in words. Hopefully you'll be able to visualize this. A equals m1g minus m2g is F net divided by m1 plus m2, the total mass of the system. Okay, table and pulley. So there may be friction here on the tables as blocks being dragged across. This hanging block is heavy enough to overcome the friction. And so what happens is it accelerates down because the force of gravity is greater than the tension. A lot of students will make the mistake and say, well, if this is 20 newtons, this is being pulled by 20 newtons because that's what's hanging here. No, no. If this were pulled with 20 newtons, then this would be 20 newtons also. And this block would have 20 newtons and 20 newtons and it wouldn't go anywhere. So this is 20. Maybe this is 18, which is what pulls forward here. This is pulled forward by 18, not 20, the gravity here. So whatever this is pulled with, it pulls back. Newton's third law, action-reaction, the tensions. And then as this is being dragged across, there is a friction here, as I mentioned, in gravity and normal force here. Balance because the block isn't falling or rising, the block on the table. So if you wanted to use what I call the shortcut technique, in other words, not draw a system of or write a system of equations, you would say this is all one giant object, you know, string and masses all together. And F net would be m1g minus mu F normal for this block. Forward force minus the backwards force is F net. All divided by the mass of both of these together, m1 and m2 to get added together. Fg minus force of friction over m1 plus m2 equals acceleration. This one I didn't go over yesterday. The incline and pulley. When we studied in class, I put quotation marks around a title and I called it Atwood's incline. I didn't know what to call it, but basically this shows up not very often, so that's why I kind of didn't review it yesterday because, you know, if this looks complicated, again, review. Go ahead and skip things that look like they're beyond you and try and look at a topic and say, what are the main ideas? What are the ones that are most likely to appear? This kind of stuff, all these other ones, more likely to appear. This I might ask a question on once every 10 years. So it's not a bad gamble to skip it. And again, even if it shows up, you only need 70% or 68% of the test correct to get a 5 out of 5. So even if you don't study things and they do come up, you're probably not going to get harmed by much unless you skip like the whole topic of energy. Well, then that's not a good idea, okay? So that's one of the big topics. All right, so here we are. We've got an inclined plane and a hanging mass. This I put in stars because if this x component of the gravity here is greater than the weight here, this will tend to slide down the hill and this will rise. But if this x component is smaller than this gravity, then this will tend to go down and this will rise. So you don't know which way. Here it's easy to see. This is bigger. It's going to go down, right? More massive. Here you can't tell. You got to find that x component and compare it to the weight here. So it might be F net is this minus that, or if this is going down, then F net is that minus that. Okay? All over the total mass. Okay, so those are different scenarios. Again, they can always dream of something else that's not on this sheet. AP sometimes does that. They get creative. They ask questions that you haven't seen before, but those are the highlights. All of those force diagrams, you know, as I wrote here, and I already explained, they're used in Newton's second law. A is F net, which is usually, you could just think of it as forward force minus backward force over the mass. Okay, so that's F net over M. Different things are possible. If, for example, the forward force is bigger than the backward force, then the object will accelerate in speed and gain velocity. Maybe it starts at rest, then with an acceleration we have a parabolic x graph, a linear velocity graph, and a constant acceleration. So you see, we could have kinematics, that's my point here, mixed in with Newton's laws. You might have to, part A, get the acceleration, part B, draw some graphs, or possibly even use x equals x0 plus v0 t plus 1/2 at squared, one of those formulas, to figure out where it is or its velocity. Kinematics can and often is mixed in with Newton's laws. Okay? Also, the acceleration might not even be constant, but in all the cases that I showed you, the acceleration did turn out to be constant. Okay? Another possibility is that the forward force and the backward forces are equal. Okay? So maybe I'll zoom in a little bit so you can see a little bit better. And as I explained, that means two things are possible. The object staying at rest, constant x, zero velocity, zero acceleration. Another possibility is the object's moving at a constant velocity. Notice zero acceleration also, because F net is zero. Forward minus backward. I guess I got 15 newtons forward, 15 backwards. Balance F net is zero. Acceleration is zero. But instead of staying at rest, we might be moving at a steady velocity. This is also delta V over T is zero. Delta V over T is zero. Constant velocity or at rest, both mean zero acceleration, force is balanced. So don't forget this, that when the force is balanced, it could be moving at a steady velocity. A lot of students do. They say, oh, it's at rest. Well, maybe. And then the other possibility is that maybe the forward force is smaller than the back. We got more backward force. Hey, that's possible. People say, oh, then you're going backwards. No, not necessarily. If you're going forward in your car and you've got your gas pedal down and then you start hitting a deep snowbank, so your car is still going forward, and your tires are pushing, right? Pushing your car forward, but the snowbank has more backwards drag than the forward force of your tires. You continue to move forward and slow down. And so the way we show that is that slowing down is by decreasing the slope of this graph. In other words, we create a curve, a parabola that's leveling off. Well, the snowbank example is a bad one, but because eventually the backwards, if it continues, it keeps going, then in the negative direction starts speeding up. So slowing down and then going forward, slowing down, then backwards speeding up. That's force diagram when the backwards force is bigger the entire time. Maybe wind would be a better thing than the snowbank. All of a sudden a hurricane hits and you know 200 mile an hour winds or something, and then so you eventually get pushed backwards. Velocity goes from positive to negative, straight line. The entire time the acceleration is negative. When you're slowing down and speeding up, people say, oh, now you have negative acceleration then positive when you start speeding up. No, we're speeding up in the negative direction. We're slowing down in the positive direction. Both of those are negative accelerations. So that's it. The big giant concept map of all, or a good deal of a good portion of the ideas within Newton's laws unit. Again, look at this. It's another way to review Newton's laws. Maybe this is better for you in terms of more concise than the notes yesterday, but review all you can. Keep up with the review. Keep up with the problems. And I'll see you in the next video, which will be on energy. So see you then.